We have kind of tried to introduce you to energy modeling and how the various parameters used in energy modeling can actually help you to aid important decision making in your detailed design stage. And now we look at actually a case study of an actual building which we had done, and where the client had asked us to actually create the simulation studies or energy simulation for a particular office building. They wanted to locate the building in 3 different climate zones and see how the performance of the building would be. They didn't want to change the design. So the design would be the same, but what would be the impact of locating the building in different locations? For example, in India, you have different climate zones. So we are trying to, we'll tell you how this building, if you locate it in different locations, the same design, how it's going to perform. So that's something that you can look at and see where you want to locate the building, right? So we chose 3 different climate zones: hot, humid, moderate, and hot, dry. Hot, humid is basically Chennai, which is a coastal area. A moderate climate zone was for Bangalore, and hot, dry for Ahmedabad. So these 3 locations were chosen, and you were asked to do a study on how the building performance would change, because they had a very clear idea of not to change the design of the building and yet see how the building is going to perform in these climate zones. So basically, here we're talking about the various parameters of the building: the area, the conditioned area, the window wall ratio. All those parameters are provided. It's a 12-floor building, and here we are talking about the different modeling inputs that we would give to that building. So what kind of envelope do you use? What is the property of the roof, the wall, and so on, and the glass, the material. So here we are trying to look at only those parameters which would influence the building envelope. So as I said earlier, modeling has a lot of parameters you can play around with. So here we are looking at only the passive design strategies which you would want to adopt for this particular building in different climate zones. So we would look at basically the window wall ratio, the SHGC of the glass, and keeping all the other parameters constant. If I just keep changing the window wall ratio, the glass property, or the wall property, we will see how the building is going to perform in these different climate zones, and that will give a fairly good idea on what material you would want to choose in a particular climate zone on a particular facade, for example. So all these studies will actually help you to arrive at the right kind of decisions when it comes to, these are all very practical case studies, which is actually a real-time case study, and these results actually were extremely useful for the customer to actually decide what kind of material to use, or which orientation you want to put the building in, what climate zone you want to put it in, right? So it actually justifies your decisions based on a lot of scientific studies, right? And we keep all the other things constant, right? We are talking only about envelope design, right? So you keep the HVAC system the same, you keep the fan power the same, chiller parameters the same. So you try to just play around with the envelope and see how your performance is going to be, right? So, and of course you can still model your systems based on the climate zone. You can still change the systems slightly and then see the impact of the envelope. So here we basically kept the systems more or less the same, since the temperature profiles were more or less the same, but except for the climate zone where you had more humidity in certain places and so on. So only the envelope parameters were changed, and then we saw how the impact of that was when it came to energy performance. So here you're looking at the different options that we had to evaluate, right? So you have the top table is talking about the glass specs. You had different varieties of glass which have different U values, different SHGCs. We spoke about U value, we spoke about solar heat gain coefficient. The VLT is talking about the visual light transmittance, is the amount of visual light that the glass would allow inside, which means it has a direct impact on the amount of daylight that you will get inside the building, right? So as you can observe here, as the SHGC gets reduced, your VLT also goes down, right? So which means you are trying to balance the two, because the more the SHGC, the more the heat that's going to come inside the building. So you want to keep the heat content low, at the same time you want more light, right? You want the best of both, and that's a challenge for most glass manufacturers, to make sure that you have a lower SHGC and a higher VLT. So we want both, the best of both, right? So now that's not possible humanly, right? You cannot have both parameters favorably poised. So we try to see how you can still reduce one and try to maintain the level of daylighting depending on the sun path and so on. So you have a fairly good idea on combining the glass with the solar window and the solar path analysis, and see where optimally you can put this glass, which facade you can put, so that you get a fairly good idea on minimizing the SHGC. At the same time you get more daylight, right? So that's the philosophy. And of course you have wall also in your envelope. And what is the different types of wall that you can look at? You have an Araucon block wall which has a lower U value compared to a solid block wall which has a higher U value. So you want to limit the U value, because lower the U value, the lower would be the heat ingress through conduction. So if you look at this slide, the next slide is talking about the climate zone impact. So what if I keep all the glass and the wall the same and just alter the climate zone? So here you can see, if I keep every parameter the same and simply change only the climate zone, everything else about the building is the same. So then what is the performance? How do you see the energy performance? So you can see the warm humid zone, which is Chennai, has got the highest energy consumption, right, with these types of glass. So if you have a wall type 1 is talking about a glass spec of ET125 with a U value of 0.352, SHGC of 0.23 and a VLT of 23%. That is glass type 1. Wall type 1 is 200 millimeter solid block. So you can see in this, from this table, that the climate zone actually has an impact on the energy performance. So warm humid climate zone actually has higher energy performance for the same spec of wall and glass compared to humid or moderate, right? Similarly you have, so you are keeping everything else the same, right? Of course you need to optimize the others also, but just to get an idea of how the energy performance varies just by altering the envelope, right? So similarly you can change the wall and then see how the energy performance is. So if you look at the top value and the bottom table, you can see that in the warm humid zone itself, your energy performance is going up when you are shifting to a higher WWR, which means you are having a higher window wall ratio in a particular facade from 30 to 80 you have made, and you are seeing that the energy performance actually is kind of going up, right? So there are various studies you can do with just modifying the envelope elements and see how your building performance is. So you can actually arrive at an optimal window wall ratio for that particular climate zone given your design, and then see how you can optimize the amount of glass in different facades based on the solar path and actually optimize your building design. So you can see that the next slide is talking about the window wall ratio and the climate zone impact. So as we increase the window wall ratio in different climate zones, you have different kinds of energy performance values. So as you increase the WWR in the same climate zone, your energy performance is going up, or the energy consumption is going up. So that's what is actually illustrated in the slide that follows. So we have just tabulated the values of the various glass types and the wall types, and how the performance of buildings actually changes when we alter these parameters. Similarly, you can do the same study for different types of glass. So if you look at the next slide, you're talking about just varying the glass type, right? So keeping the wall the same and the WWR the same. What if I change the glass? So if I change, say, to a lower SHGC glass, you can see that there is a substantial improvement in your energy, right? So at the same time, you are also not impacting the daylight. So you can actually do, you can combine these simulations, which are energy simulations, with the daylight simulation, and see, you can match the two and see how you can actually improve your daylight at the same time use a lower SHGC. So that involves a lot of studies on sun path and trying to align your building to the right kind of orientations, so that you get the optimal light inside the building, right? So all these studies can actually give you a fair bit of insight on what to use, what type of material to choose from when you do your energy studies. Fairly powerful, and with the amount of extent of weather data that's available today, we have actually a fairly accurate prediction of the energy performance that we can look at. So the next slide is talking about the wall performance. So what if I keep the glass the same and start changing the wall U values? So that gives you some fairly good idea of the incremental benefit that you will get by changing the wall alone, keeping the glass the same, right? and the WWR the same. So all these studies can actually give you a fairly bit uh, accurate prediction of the incremental benefit that you will get. For example, you can see that there is a 1.75% improvement in savings if you use a glass type 2 versus a glass type 1, or a different WWR. So these studies will actually help you to arrive at prudent decision making during your design process. So just try to summarize the value, but what is presented here is a fairly toned down version of actually what was presented to the client. We're just trying to give you some basic idea on how you can tweak these parameters to give you some to help you to aid decision making. So that's the idea of this exercise. So it's actually fairly a bit more involved. It has a lot of parameters to work with. Just try to cut down some of it and try to just give you some basic idea on what you can do with these tools and make your design decisions more effective, and how you can combine these tools with and manage your various stakeholders in the building life cycle to make sure that they are all in line with what you are expecting as an owner or a building important stakeholder in the building design. So to summarize, we have tried to see how energy modeling should not be treated as an additive to design. It should actually be part of the integrated design, and it should go along with all the phases of the building life cycle, starting from pre-design to schematic design to detailed design, all through construction, and see how your building performance changes as you elaborate the design. So it's extremely important, and on top of that, you continue to use this model during the operations as well, and try to retrofit your model or calibrate your model continuously to the actual energy performance based on utility bills that you get during your operations. So what happens is, throughout the life cycle of your building, this model is evolving and it's always calibrated to the actual performance. So tomorrow when you do an energy audit and you are finding certain energy conservation measures, you can actually put these energy conservation measures into the model to see actually how much benefit do you get, and you can start looking at cost benefit analysis and what is the percentage savings you will get. All those things can be done for every retrofit that you intend to do during the operations of the building. So that makes it even more effective. So I hope we have tried to give you a fairly good understanding of the basics of energy modeling. It's a fairly involved subject. It's got a lot of branches and various areas where you can focus on depending on your area of interest, and I hope you had a good fairly good understanding of this process and the various parameters involved in energy modeling. Thank you and all the best.